Having talked about the file system allocation methods, we are now ready to start talking about directories. Perhaps you already know that inside our disks, all the files are organized within directories and subdirectories. The information about all the files is kept in the directory structure. This directory structure also resides on the secondary storage. So essentially, a directory is also implemented as a file. This directory will consist of entries corresponding to files that belong to the directory. Each entry in the directory typically consists of the file name and the location of the index node for that file. Optionally, there could be additional metadata or meta information about the file. File itself is an abstract data type. To define a file properly, it is important to consider the operations that can be performed on the files. Now here are the 6 basic operations that need to be supported by the files or for the files. So the first operation here is creating a file. Creating a file is basically a two-step process. The first step is to find the space in the file system where this new file would be allocated, and then the second step here is an entry for this new file must be created inside the directory. The second operation here is writing into a file. To write into a file, we typically make use of a system call. This system call specifies the name of the file where we want to write and the information that needs to be written into this file. Using this information, the system will search the directory to find the file's location. Typically, the system will keep a write pointer to the location in the file where the next write needs to take place. The write pointer would then be updated whenever a write occurs. The third operation here is the read operation. So again, to read a file, first we'll search the directory for the associated entry of that file, and the system also typically keeps a read pointer to the location in the file where the next read needs to happen. Once the read has taken place, the read pointer is updated. Note that since a process usually either reads from a file or writes into the file, the current operation location can be kept as a per process current file position pointer. Now both the read and the write operations will use this same pointer. This basically saves space and also reduces the system complexity. The fourth operation here is repositioning within a file, which is also known as a seek operation. So for repositioning within a file, again the directory would be searched for the appropriate entry, and then the current file position pointer, right, this pointer that we talked about, this would be repositioned to a given value. Repositioning within a file does not typically involve an IO. It need not involve an IO operation. The fifth operation is deleting a file. To delete a file, essentially we search the directory again for the file that is named. After finding this associated directory entry, we release all the file space so that it can be reused by other files, and we erase the directory entry. The final operation here is truncating a file. So you see, sometimes a user may want to erase the contents of a file but keep its attributes. So this truncate function or this truncate operation basically allows all the attributes of the file to remain unchanged, but it lets the file to be reset to length 0 and all its file space be released. So all the content of the file is deleted essentially, but this empty file with its attributes would stay inside your directory. Let's now take a look at how we can implement some of the common file operations. So the first operation we'll walk through is renaming a file. Let's say we have a file called foo.txt in the current directory or in any given directory, and we want to rename this to, let's say, foo1.txt. So here are the steps that would be followed. First, we will read through the directory where this file foo.txt resides, and we would make sure that this new name that we want to use, foo1.txt, is unique inside the directory. So this is the second step. If this foo1.txt is unique, then we'll find the entry for this file foo.txt inside the directory, and then we'll change the name of this file from foo.txt to this new name foo1.txt. Note that when renaming a file, the file contents are not modified. The next operation is, let's say we want to move a file from one directory to another directory. So let's assume we have these two directories D1 and D2. Inside both the directories we have a bunch of files. We have this file foo inside directory D1, and we want to move this file foo from D1 to this directory D2. So here are the steps that we'll follow. First, we will read both the source and the destination directories. So we'll read both this directory D1 and D2. Essentially, to move this foo to directory D2, we need to make sure that this name foo is not currently already in use inside this directory D2. So we have to make sure that there is already no other file with name foo inside D2. If that is true, if foo does not already exist inside D2, which is the case here in this example, we can find the entry in the source directory. So we'll find an entry for this file foo inside the source directory, and then we'll copy this entry from directory D1 to directory D2. So recall that the directory entry for file foo inside D1 would contain the file name and the location of its inode. So we'll copy this information from here to inside directory D2. So let's say we create another entry here for foo and copy this inode information. After copying this information to directory D2, we can delete this original entry in directory D1. This is how we will move a file from one directory to another directory. Note that the file itself is not modified. The contents of the file are not modified. We have just copied the directory entry of the file from one directory to the other directory. Next, let's say we want to copy a file from one directory to the other directory. So let's say we have this file foo inside directory D1, and we want to copy this file to directory D2. So once again, we'll start by reading both the source and the destination directories. Again, we need to make sure if we want to move this foo, we need to ensure that currently there is no file with name foo in directory D2. If not, then we can start the copy process. However, if there is another file with the same name in directory D2, then we may need to prompt the user to ask whether we want to overwrite this file or we want to cancel the copy operation. So let's assume that right now there is no existing file foo inside directory D2. So we can start the copy process. We'll first read the inode associated with the file. So this is, let's say, inode 1 here. To create a new copy of this file foo in directory D2, we would need to create a new inode. So let's say we create this inode 2, which would be the inode for a copy of foo in D2. Some information into this inode 2 can be copied from this original inode in directory D1. However, not everything would be copied, because this is an inode for a new file, which is a copy of file foo. So it will have its own different inode number, it will have a different inode block, and so forth. Now we can create a directory entry for this file foo in this directory D2. So we have the file name, and we will store the location of the inode for this copy of foo in D2 here. After this, finally, we will create a new copy of the data blocks which originally belonged to this file foo inside directory D1. Next, let us look at how operating systems implement some of the simple file operations like opening and closing a file. Like we have seen, most of the file operations, they involve a search through the directory for the file that we are working with. So to avoid this constant searching, many systems require that an open system call be made before a file is first used actively. So here is a brief description of what happens when we make a the open system call. So this open system call, this takes a file name and searches the directory, and then it will copy the directory entry for this file into an open file table. So that is basically a table in the operating system which keeps track of all the files which are open in the system. The open system call will typically return a pointer or index to the entry corresponding to this particular file in the open file table. In the Linux operating system, this pointer is known as a file descriptor. This pointer is typically not the actual file name. However, it is used in the future system calls which are made after subsequent to making the open system call for accessing the file. So this basically using this pointer that was written by the open system call, this basically avoids further searching through the directory, the repeated searching, and it also simplifies the system call interface. Note that in our modern operating systems, it is possible that the same file is opened by several different processes simultaneously, and therefore the operating systems maintain two different tables or data structures for managing all the open files. One is a global open file table and the other one is a per process open file table. This global open file table, this is a system wide table. So it contains an entry for every file that is open in the system by at least one process. Now this global open file table, this contains process independent information about the files that are open. So for instance, it can have information like the location of the file on the table of, the location of the file on the disk, the access dates, the file size, and so forth. Now once a file has been opened by at least one process in the system wide table includes an entry for that file. Now the other thing you should remember is, regardless of the number of processes that are working on a given file, there would only be one entry per file. So it is possible that, let's say we have a file foo and let's say 6 different processes are reading from this file. Still, there will be only one entry for this file foo in this global file table. Now in addition to this global open file table, for every process we have a per process open file table. So each process has its own per process open file table. In contrast to the global open file table, the per process open file table contains the open file information that is specific to the given process. Now let's quickly talk about the contents or the information that is stored in the global open file table and the per process open file table. So like we have seen, the global open file table will have an entry for every file that is open or in use by at least one process across the system. Like we have seen, this file table contains information independent of the processes that are accessing the file. So for example, it will contain like the size of the file, the access dates for the file, the location of this file on the hard disk, and also if there are multiple processes that are accessing the file, then it will have a count of the number of those processes. So essentially number of times a file is open in the system or the number of processes that are accessing this file right now. So for example, if processes P1, P2 and P3 are accessing a file foo simultaneously, this would be 3. The count would be 3. Now in contrast, the per process open file table, it contains information about all the files that a given process has open. In this table, we store information regarding the use of the file by the given process. So here we'll find information like current file position pointer. So this is basically the pointer to the next read write location for the given process. So for example, let's say we have this file foo and process P1 is reading or writing into this file, and let's say currently process P1 is reading at this point in this file. Let's further assume that several other processes are also simultaneously accessing this file foo, and so for in the per process open file table for process P1, let's assume that this is the per process file table of process P1. We'll have an entry for file foo, and in this row or this entry we'll have one of the informations we'll have is a pointer to this location where a pointer to this location where P1 is reading or writing into foo. So basically we'll have this pointer is stored over here. The other piece of information is the access rights. So for example, can process P1 only read into the file, or is it also writing into the file, and so forth. And finally, recall that in our global open file table, let's say this is our global open file table, here also there would be entry for there would be one of the entries would be for file foo, and this entry for foo in global open file table will contain process independent information like for example the size, the disk location of the data for this file. So the process P1 actually needs access to this data that is stored in this global open file table, and therefore there is also a pointer is stored here in this per process file table to the entry in the global open file table for foo. Note that in order to read or write into this file foo, we need to know where it is located on the hard disk, and this piece of information is stored in the global open file table, not in the per process file table, and that is why we need this pointer from the per process file table entry of file foo to its corresponding entry in the global open file table. So this picture over here illustrates how a typical read operation would work in our operating systems. This is a read on a file, and we are assuming that the operating system is storing two different file tables. It has a per process open file table and a system wide open file table. For the sake of this example, let's assume that we are interested in reading file foo. So the way this works is, in the user space or the user program, we'll make a read system call for reading this file. To this read system call, we'll pass an index. Now what is this index? Recall, before actually reading the file, we need to open the file foo using this open system call. Now this open call returns a pointer or an index to the appropriate entry in the per process file table. Okay, so this is that index which we are using here with the read system call. So using this index, we will look up the entry for file foo in the per process open file table. Recall, this entry for file foo in the per process open file table will contain a pointer to the corresponding entry for file foo in the system wide open file table. So now we will use that pointer stored here to look up the corresponding entry for file foo in the system wide open file table. Now it is from here, from the entry in the system wide open file table for file foo, that we will get the necessary information to access the actual file data that is stored on the hard disk. So the way this works is, this entry for foo in the system wide table would actually contain a copy of foo's index node or the file control block. Now recall that this index node has the pointers to the actual data blocks which are stored on the hard disk. So from here we can access foo's data and read it. So this is a summary of how a read operation for the file would work. For reading or writing the file, there are two different access methods. We can either do sequential access or direct access. Sequential access reads or writes the file in sequence from the beginning. So for sequential access, we'll have a pointer which keeps track of the current location where we are reading or writing into the file. A read or write operation which is issued on the file is always based on the current location of this pointer. So many systems do allow this pointer to have a seek movement. So essentially what this means is, we can move the pointer ahead or behind without actually reading or writing. So that's a quick summary of sequential access. For direct access, the file is divided into several records, and a direct access is provided for each record. So for direct access, when reading and writing, each read and write operation must specify the record number which we are interested in reading or writing. This kind of direct access is typically used in reading and writing the databases, which are very large and they rarely have a sequential access. So what I mean by that is, information stored in a database is rarely accessed in a sequential manner. And finally, the close system call can be used to tell the operating system that the process no longer needs a given file, and so we can close the file. Note that the files are automatically closed if the process terminates. So all the files that this process had open, those files would be closed for on behalf of this process. For now, let's assume that we are using a close system call for closing a file. So in this case, the following actions are carried out. So the first thing we'll do is we'll remove the entry for that file which we are closing from the per process open file table. So for example, let's say in process P1 we had this file foo open, and now process P1 no longer needs access to file foo, and so we are closing this file foo. So there would be an entry for foo in this per process file table for P1. So we'll remove this entry corresponding to foo from here. So this will be deleted. Entries for other files which P1 may still need or which are still open for P1, they would remain intact in this table. Now after removing foo's entry from process P1's per process file table, the second thing we will do is we will now decrement the open count for file foo in the global file table. So recall, there is an entry for file foo in the global open file table as well, and one of the fields in that entry is the open count, right? So this open count indicates how many processes are using this file right now. So because this file was closed by process P1, let's say previously this open count was 3, so now it would be decremented by 1 and now updated to 2. So only 2 more processes have this file foo open. P1 has closed it. If it so happens that on decrementing the open count, this count reaches 0, it means the file is no longer in use in the system, and therefore the file's entry is removed from the global open file table as well. Alright, so that basically brings us to an end of file systems. We'll now switch gears and start talking about virtual memory in our modern operating systems. So let's get started with an introduction to memory management. Here we'll look at questions like where an executing process resides inside our computer systems, how an executing process is laid out in the main memory, how do we allow multiple processes to share the same main memory. We would also look at the notion of a memory address, and we'll see how a memory address is actually interpreted. Later, we will revisit this concept from a hardware perspective and what an address looks like and how the operating systems deal with it. So these are some questions that we want to answer in this section. This picture over here shows one possible way in which processes may reside in the main memory. So here we are going to assume that the memory itself is laid out in addresses from, let's say, starting from address 0 to some address n, which is n equal to 2400 in this case. So essentially the memory can be viewed as a contiguous array of several bytes or words. For now, we are assuming that the operating system is loaded in the RAM at all times. Besides that, we have these three processes A, B, and C, which are also loaded in the main memory. In this case, we are assuming that each process is laid out contiguously inside the RAM, right? So you see the entire process A is here. Similarly, entire process C is here, and so forth. A given process is not spread across uncontiguously in the main memory in this example. Later we will look at some other possible ways of representing processes in the main memory which may not be contiguous. In this example, these gray regions over here, these are unallocated or free regions of memory. So in this example, the operating system is occupying first 400 bytes starting from address 0 to 400. Process A is occupying the next 500 bytes starting from address 400 to address 900. Then there is some free chunk of region from 900 to 1100. Then process C is occupying these 300 bytes from addresses 1100 to 1400. And finally process B is occupying these last 400 bytes from address 2000 to 2400. So with this given layout, let us define some terms. The first term here is a segment. So a segment is basically a contiguous chunk of memory that is allocated to a process. So for instance here, if you look at this, this is a segment, right? So addresses 2000 to 2400, these are allocated to process B. So this is one segment. Similarly, if you look at here, we see that addresses 400 to 900, these are allocated to process A. So this is another segment of memory, and so forth. Next, physical address is a real memory address in the main memory. In this picture on the right side here, these are physical addresses, right, going from address number 0 to 2400. So for example here, let's say we look at some address 1500 over here. So this 1500 is an address that belongs to an actual byte or word which exists inside this RAM in the hardware. In our discussion, we will be distinguishing between a physical address and a virtual address. A virtual address is basically an address relative to the start of a process's address space. So for instance, let's look at this process A over here. So on the left hand side here in this picture, we have virtual addresses. So let's zoom in on this process A. So this process A, the virtual addresses of this process A, it goes from address 0 to 500. So essentially this process A has 501 bytes, let's say. And on the right hand side we have these physical addresses, and note that on the main memory, the actual physical addresses where this process A is stored, it basically starts from address 400 and goes all the way to 900. So if you look at some of the bytes inside this process, so this topmost byte is a virtual address 0, then we have a virtual address 1, 2, and so on, right? So this this byte that has a virtual address of 2, this is the third byte within this process A. But this 2, this is the virtual address of this third byte inside process A. If you look at the physical addresses, the actual address in the main memory where it is allocated, that would be, you see the first address is 400, the next address would be 401, and the address of this third byte would be 402. So this virtual address 2 inside this process A, it translates to physical address 402 on the physical address. Now another way of thinking about these virtual addresses is when a given process or a program is translated by a compiler and an assembler, these translators, they always assume, they make a simplifying assumption, and the assumption is when this process is loaded in the main memory, it will always start from memory address 0. Now this is a simplifying assumption, and obviously if you have a dozen different processes residing in the main memory, not every process can start from this physical memory address 0. In fact, in most modern operating systems, these lower order addresses starting from physical address 0, these are reserved for the operating system, and therefore pretty much no user process ever starts from this memory address, physical memory address 0. They all start from some higher memory addresses, I mean higher physical memory addresses. So the process or the program during execution, it actually generates and sees these virtual addresses. However, for executing the program, these virtual addresses need to be translated into the corresponding physical addresses inside the main memory. So always remember that physical address is the true or actual address that exists inside the main memory. As opposed to this, the virtual address, this is relative to the start of the process. And also remember that a virtual address needs to be translated into a physical address before accessing the main memory. So with that background, let's now think about how our programs generate these instruction and data addresses. So broadly speaking, as shown in this slide, there are three ways of generating the addresses that can be used during execution. So the first way over here is at the compile time. So here basically the compiler can generate the instruction and the data addresses when it compiles the code. The other possibility is at the load time. So essentially when we are loading the process from the hard disk to the main memory, we can fill out these addresses for the instructions and the data with the right physical addresses, because at the load time we will know where physically in the main memory the process is going to reside. So at the load time, the addresses can be generated by the loader. Or the third possibility is the addresses can be generated at the runtime or at the execution time. Let's think about each of these in some more details. So if you think about it, when you are writing your programs, you're not really dealing with the main memory addresses. You are dealing with variables and data structures. So for example, you may have an integer x inside your program. Now this x is representing a physical memory address. However, you don't this memory address is hidden from you. You don't access that memory address directly. You refer to it with the name of this variable, and you leave the details of where this variable x would reside in the main memory either to the compiler or to the interpreter. Now when the compiler compiles the code, in this case it will take all of these variables and assign them to some addresses. So this is one way of assigning or generating addresses for the data and the instructions in our programs, and that is by the compiler. Now the second possibility here is that we assign or generate the addresses at the load time. Now the reason for doing this is when the compiler was compiling or translating the code, the compiler may not know where in the main memory this process would be loaded, where a given process would start in the main memory. Now this is the operating system's job. The operating system is responsible for allocating a segment to the process. So for instance, on the previous slide, we saw that we had, let's say, this main memory, and we had a bunch of processes inside the main memory. Now, out of all of these processes, we saw that, this process C, it was laid out in the memory starting address 2000, and it went on from there. Recall that this 2000 was the physical address from where the process C was starting. But note that when the compiler was compiling the code for this process C, it would not have known that in the main memory this process C would be loaded starting memory address 2000. It is possible that for a certain set of processes, maybe this address starting 2000 was not available, and so the operating system could have decided to allocate this process C somewhere higher up here, maybe starting from address 300 and so forth. The point here is it is not possible for the compiler to predict where in the main memory a given process would be allocated, and therefore what we can do is we can defer generating the physical addresses to until the load time when the process is actually loaded from the hard disk into the main memory, and the compiler at the compile time can simply generate the virtual addresses. So recall the virtual addresses are generated starting from address 0 to some value n depending on the size of the process. So the compiler will make this simplifying assumption that the process will start from address 0 in the main memory, and it will only generate virtual addresses is relative to the beginning of the process itself. And later on we will let the loader translate each of these virtual addresses into the corresponding physical addresses. So when we are loading this program from the hard disk into the main memory, we'll look at each address, we'll see where each virtual address is actually residing in the physical memory, in the main memory, and we'll accordingly translate the virtual addresses into corresponding physical addresses. So this is the second way of generating addresses at load time. The third possibility is the runtime or the execution time. Now this third possibility or this third scenario is what we will talk more about. So we have seen that the compiler doesn't know where the process will be loaded in the main memory, so it only generates the virtual addresses. Now once the process is loaded in the main memory, we will use some hardware to translate these virtual addresses into physical addresses on the fly at the runtime. So to understand how to translate from the virtual to the physical addresses, we will see an example just in a minute. Before we dive into some actual techniques for translation, it is important for us to realize that we have a multi-programming environment. Multiple programs are residing in the main memory simultaneously. Our memory is shared, and therefore it is important that the memory management techniques in the operating system achieve these three properties for us. The first requirement here is transparency. So transparency basically means that multiple processes should be able to coexist in the main memory. However, The processes should have an illusion that they are the only ones. Every process should have this illusion that it is the only one in the main memory. So essentially no process should be aware of the existence of other processes in the main memory. And transparency also means that a given process should not care what portion of the physical memory it is assigned to. So essentially uh, the actual physical addresses where a given process is located or assigned should not affect the program logic or program execution. The second important desirable property from our memory systems is safety. So safety basically means that the executing processes that are coexisting in the main memory, they should not be able to corrupt each other's data. So one process should not be able to access or modify memory addresses in some other processes memory address space. The safety property also means that the executing processes must not be able to corrupt the operating system. And finally, the third desirable quality from the memory management subsystem is efficiency. So essentially what this means is we don't want the performance of the CPU or the main memory to be impacted because of the memory management features. So for instance, the performance of our CPU and memory should not degrade badly because of the fact that the main memory is shared between so many processes. So recall, towards the beginning of this discussion in this subsection, we looked at a picture which showed a simple memory allocation scheme where several processes were contiguously laid out in the main memory. Now, though it represented a simple memory management scheme, such schemes are not typically used in practice because they have several issues. So let's now try to understand what might be the issues with such schemes. So for this example, let's go back to our earlier memory system where memory addresses go start from address 0 and go on up to 2400. So these are the physical addresses. So let's try to understand in this memory for our simple memory allocation scheme, what might happen, how the main memory will evolve as the processes come in, execute and depart the system. So let's assume at the beginning we have in our main memory the operating system and processes A, B and C, all of them allocated contiguously as shown here. So for simplicity, let's assume that this operating system is occupying the first 400 bytes. This process A is occupying the next 500 bytes here. Process B is occupying the subsequent 900 bytes, and then process C is occupying next 300 bytes here in the main memory. And this shaded region over here, this is the free memory, free chunk of memory. So in some time, let's assume this process B finishes execution and it leaves. So we now have this 900 bytes free memory region where B resided. Note that the piece of memory which is free for allocation is known as a hole. So these shaded regions here, these are holes. These are free pieces of memory that can be used for allocating any new incoming process. Now let's say after B departs, uh, in some time process D arrives. So we allocate space to this process D out of this hole that was created by process B. So D now occupies the 600 bytes here, and so the hole has shrunk. So we have this 300 bytes of hole here, addresses 1500 to 1800, and we have this 300 byte of hole from previously. Now let's say in some time process A also finishes, so we now have this new hole of 600 bytes over here. So in the last snapshot in this picture, we have a 600 byte of hole, then we have a 300 byte of hole here and a 300 bytes of hole here. So essentially over time, as processes arrive and leave, our main memory would be fragmented or divided between several chunks of memory that are free and then chunks of memory that are allocated or occupied. Now in this system, whenever a new process comes in, we will need to find a hole or basically a contiguous free chunk of memory which is big enough to accommodate the incoming process. So for instance, if a new process E were to come in now at here, and let's say process E has a size of 100 bytes, then we need to find a hole here that can accommodate this process E, which is big enough, which is at least 100 bytes large. So this is a quick summary of how contiguous allocation works. Now note that in this discussion, for now we are assuming that the processes are not moving around in the main memory after they are allocated to a certain spot. Note that if multiple holes can accommodate an incoming process, then it is the responsibility of the operating system to decide which hole is used for accommodating or allocating the new process. Let's quickly think about, given a new incoming process, how the operating system would decide which hole to allocate this process in. Recall when we were talking about contiguous allocation of files on the hard disk, we talked about first fit, best fit, and worst fit. These three methods can be used for allocating memory even for processes in contiguous allocation. So for instance, let's say we have a new process E that requires, let's say, 300 bytes. So the first fit allocation policy says that for this new incoming process, we'll go through this list of holes in the memory sequentially, and the first hole, which is big enough to accommodate this new process, will be used. So in this case, for example, this is, let's say this is our first hole, this is the second hole, and this is the third hole over here. So the first hole is 500 bytes. So clearly 500 bytes is big enough to hold this 300 byte process. So first fit would simply use this hole. As opposed to this, the best fit policy, recall, it tries to find the tightest fit. So the best fit says that we'll go through all the holes in the main memory, and the smallest hole, which is big enough to hold the incoming process, would be used. So essentially the tightest fit. So in this case, the incoming process requires 300 bytes. So both these holes, the last two holes, second and third, are big enough, or the tightest holes that can accommodate the process E. So either of these two can be used by the best fit. As opposed to this, the worst fit, recall, it says that the largest hole which is available for accommodating the incoming process, that should be used. So in this case, the largest hole would be the first hole, which is 500 bytes. So we have already talked about these allocation policies earlier. So the same first fit, best fit, and worst fit policies can be used for contiguously allocating memory to processes even in the main memory. Recall, we also looked at the problem of fragmentation in contiguous allocation. There are two types of fragmentation: external fragmentation and internal fragmentation. Unfortunately, both the problems will exist here as well in contiguous memory allocation. So recall, external fragmentation exists if in aggregate there is sufficient free space in the main memory to house the incoming process. However, there is no one contiguous hole or chunk that is large enough for the incoming process. So for example, let's say we have this incoming process F, which requires 600 bytes. So note that right now, if this is the state of our memory, we have these three holes, 1, 2, and 3, 500, 300, and 300 bytes. So in total, we have 500 plus 300 plus 300, 1100 bytes that are free in the main memory. So clearly, 1100 bytes should be sufficient to accommodate this incoming process F, which only needs 600 bytes. But unfortunately, none of the three holes are 600 bytes or above, right? So the largest hole that we have here is 500 bytes, which is not enough to accommodate the incoming process. So this is an example of external fragmentation. Now, as opposed to external fragmentation, the internal fragmentation exists when we allocate a chunk of memory to a process which is bigger than what the process needs. So essentially, the process will not be using all the memory which is allocated to it, and therefore some of it is wasted as internal fragmentation. So let's take a quick example to understand this. So let's assume that we have a new incoming process G, and let's say this process requires only, let's say, 298 bytes, and we are using the best fit algorithm. So we run this best fit to figure out where to allocate this new process G, which requires only 298 bytes. So let's say the best fit algorithm, it chooses this third hole over here for allocating G. So note that if we allocate G over here, this hole has a size of 300 bytes, right? So if we allocate exactly 298 bytes to process G, we will have a very small hole of 2 bytes left here at the end of the third hole. Now the problem is, if we keep track of this 2-byte hole, it is practically useless for any incoming process, and therefore it is practically more efficient to simply allocate this extra 2 bytes to the process G itself, as opposed to keeping track of it in the free holes list. So in this case, these 2 bytes that are allocated to process G, but process G doesn't need it, and so would not be using these 2 bytes, these are wasted as internal fragmentation. So having talked about external and internal fragmentation, this slide over here basically summarizes these for us. Most of this we have already talked about on the previous slide. One additional thing that I would like to point out here is, experiments have shown that over time, if we allocate 2n blocks using contiguous allocation, roughly n blocks are lost due to external fragmentation. So essentially 1/3 of the memory space would be wasted in external fragmentation if we are using contiguous allocation. Now this is an empirical result that has been observed in experiments. This is not a law, it's more of a heuristic. Now here is a quick summary of some of the significant bits that you should remember moving forward. So the first is, you should remember that in order to execute, a process must reside in the main memory. And the second important bit here is, during execution, the processes generate or they see virtual addresses. These virtual addresses need to be translated into their corresponding physical addresses before accessing the main memory. Now the way this translation happens from virtual address to the physical address on the fly is what we will talk about shortly.